Good day, ladies and gentlemen. You're welcome to Apex Easy Learning. I'm by name Pisan. We'll be looking at chemistry, and this aspect of chemistry will be dealing with inorganic chemistry. And the topic we'll be looking at is quantum number. Different scientists have tried to explain the structure of atom right from the J.J. Thomson, who explained the structure of atom as a sphere of positively charged matter with electrons embedded within it. Also, we have Ernest Rutherford, who explained the structure of atom, comparing it with a miniature solar system. But Niels Bohr proposed a quantum theory which explained the positions of electrons around the nucleus of an atom. The Niels Bohr proposed a quantum theory which explained that electrons occupy a certain energy level, which he called quanta. That electron always possessed a fixed amount of energy. And this quantum theory explains how electron is distributed around the nucleus of an atom. We have four different quantum numbers as explained by Niels Bohr. The first quantum number, principal quantum number. The second one is azimuthal quantum number or subsidiary quantum number. The third one is magnetic quantum number. And the fourth one is the spin quantum number. The principal quantum number deals with energy level. That is, electron occupy a certain energy level with n equals to 1, 2, 3, 4, meaning we have energy level 1, energy level 2, energy level 3, energy level 4, meaning electron occupy this energy level. This energy level is called shell. It's called shell. And these shells are represented with letter K, L, M, N, meaning the energy level 1 is represented with letter K, energy level 2 is represented with letter L, energy level 2 with level 3, M, and level 4, N, and so on and so forth. So meaning we say we have K shell, L shell, M shell, N shell, and the rest. This energy level have a certain number of electrons that occupy by this level. The number of electrons that each of the shell occupy is given as 2n squared. 2n squared, where n is the principal quantum number, that is 1, 2, 3, 4, and so on and so forth. So by calculations, we can have that 2n squared from there. 2n squared, if our n is equals to 1, when n equals to 1, you have 2 into 1 raised to the power of 2, which if you look at it, 1 raised to the power 2 give us 1 times 2 will give us 2, meaning the energy level 1 can accommodate 2 electrons. When n is equals to 2, we can have 2 into 2 raised to the power of 2, which will be equals to 8, meaning the second shell can accommodate 8 electrons. And when you look at the third one, 2 raised to power 2 into bracket 3 raised to power of 2 give you 18, meaning energy level 3 can accommodate 18 electrons and energy level 4 can accommodate 32 electrons, and so on and so forth. The azimuthal quantum number is denoted with letter L. You can see it deals with sub-energy level, which we also call subshell. The value of L for the subshells is 0, 1, 2, 3, and so on and so forth. 0, 1, 2, 3. And the subshell is represented with letter S, P, D, F, and so on and so forth. Meaning the value of S is 0, the value of P is 1, the value of D is 2, and the value of F is 3. Now, each shell is divided into this subshell, meaning the S, P, D, and F. The first shell, which is K shell, is divided into S, which is only one shell, meaning we have only one subshell in K shell. While in L shell, we have two subshell, S and P. The M, we have S, P, and D. While in N, we have S, P, D, and F. So in K shell, which is the first shell, the subshells we have there is 1S. While in L, we have 2S and 2P. In M, we have 3S, 3P, 3D. In N, we have 4S, 4P, 4D, 4F, and so on and so forth. Now, the magnetic quantum number M, this one deals with the orbitals in the subshells, meaning the orbitals or the subshell is subdivided into lesser sub-energy level, which we call the orbital. The value of the M ranges from minus L towards the plus L, meaning that the magnetic quantum number depends on the subsidiary quantum number. Meaning if you have the magnetic quantum number as, let's say, for instance, you have it as 1. Let's say our L is 1. If L is 1, it means our M is going to be minus 1, 0, and 1. But if our L is 0, when L is 0, it means you are going to have M to only be equals to 0. As you can see that L starts from 0, 1, 2, 3, and so on and so forth. So when L is equals to 0, M is equals to 0. So if L equals to 2, you will be having your M to be equals to minus 2, minus 1, 0, 1, and 2. Meaning you are having 5 numbers there. If L is equals to 3, meaning you will be having minus 3, minus 2, minus 1, 0, 1, and 2. So that is how we have the value of M for the magnetic quantum number. Now, S has only one orbital. The P has 3 orbitals, and that is from this magnetic quantum number you can check it very well. When L is equals to 0, we have only one value of M, which is 0, meaning we have only one orbitals there. When L is equals to 2 is 1, we have 3 value for magnetic quantum number, minus 1, 0, and 1, meaning we have 3 orbitals. When L equals to 2, we have 5 numbers, meaning we have 5 orbitals. When L equals to 3, we'll be having value of m to be 7, -3, -2, -1, 0, 1, 2, 3. That is 7 value. There we'll be having 7 orbitals. These orbitals, sometimes we represent it with box. We represent it with box. And each of the orbitals can accommodate 2 electrons. Each orbitals can accommodate 2 electrons. And the third quantum number, which is the fourth quantum number, which is the spin quantum number, explain another thing. Here we have 2 electrons that is occupying the same orbitals, always spinning in an opposite direction with a value of plus or minus half. Meaning that when we said that each of the orbitals always occupy by 2 electrons, each of the electron always spinning or rotating, we can use that word, in opposite direction. One can rotate in clockwise direction, while the other can rotate in anti-clockwise direction. If we have an orbitals represented with a box, and 2 electron is occupying that box or the orbitals. One is clockwise, the other one is anti-clockwise, meaning we draw one with arrow facing up, the other one with arrow facing down, like this. So each of the electron there, according to the spin quantum number, have a value of either plus half or minus half. So that is the spin quantum number. Now, from there, we can have this arrangement of the electrons based on all these explanations of the 4 quantum number that we have. But before we can do this arrangement, there are some theory that also govern the distributions of electrons around the nucleus or within these shells and orbitals. The first of the theory is Pauli's exclusion principle, which states that 2 electrons in the same orbitals can never have the same number for all the 4 quantum number, meaning that 2 electrons that occupy the same orbitals cannot possess the same number for all the 4 quantum number. That is, if the value of the principal quantum number is the same for the 2 of electrons occupying the same orbitals, the value of the subsidiary quantum number is the same also. The value of the magnetic quantum number may be the same as well. But the value of the spin quantum number will not be the same, since the spin value can either be plus or minus half. So that is the Pauli's exclusion principle, that the 2 electrons occupying the same orbitals cannot have the same value for all the 4 quantum number. Another rules that govern the distributions of these electrons is Orm's rule. The Orm's rule states that the electrons occupy the degenerate orbital singly first before pairing. When you hear the word degenerate orbitals, you might ask, what is the meaning? Degenerate orbitals means orbitals with the same energy level. You might come across such questions like that in JAMB. It simply means orbitals with the same energy level. So, electron occupy the degenerate orbital singly first before pairing. Meaning, if electron is to occupy the orbitals, it will first of all occupy the orbital singly first. Let's assume we have orbitals P, which is having let's say 4 electrons. If this electron are to be distributed in the p orbitals, we said we have 3 p orbitals. The electron will enter singly first. 1, 1. Then we're having one more electrons. That make it 4. So it will enter singly first before pairing. So that is the Orn's rule. So if you have d orbitals, which is having about 5 different orbitals, let's say I have d7, which is 7 electrons in d. If I distribute the electron 1, 2, 3, 4, 5, it will enter singly first, singly first, singly first, singly first, singly first. That make it 5. Then before pairing. Now, the uses of this is in case you have like P4. If you have P4 in this case, if you don't follow the Orn's rule, you'll be having this something like this. 1, 2, 3, 4. Meaning you are going to have empty orbitals. This one is anti-Orn's rule. So if you are sharing the electrons around the orbitals, you must follow the Orn's rule. Another rules there is Hofbauer principle. The Hofbauer principle, which states that electrons occupy the orbitals with the lowest energy level first, before orbitals with the higher energy level. We have different orbitals. We have, as we said, that we have different orbitals, 1s, 1s, 2s, 2p, 3s, 3p, 3d, and the rest. If we arrange it based on the Hofbauer principle, we'll be having 1s. So based on Hofbauer principle, we have this 1s, 2s, 2p, 3s, 3p, and the rest. Now, based on this all this arrangement, the line arrangement, you look at it, 1s first. After you give it to 1s, you go to 2s. After you give it to 2s, you go to 2p. Then after 2p, you go to 3s. After 3s, you go to 3p. After 3p, you go to 4s instead of 3d. Don't forget that we have 3d. Then we will not give it to 3d, you go to 4s. After 4s, then you go to 3d. After 3D, you go to 4P. Instead of you to go to 4D and 4F, you go to 5S. So this is Hofbauer principle in the order of the energy level, meaning that 3P energy level follows by 4S, not 3D, based on the energy value. So the lower energy orbitals will be given the electrons first before going to the higher energy level. Now that is Hofbauer principle. Now let's now see how this electron is arranged in shell based on all we have learned. Now, when you look at this, this is the electronic shell electronic configuration. So the arrangement of these electrons according to shell, let's quickly look at how it is done. When you have KLMN, we'll look at the first 20 elements. The hydrogen has 1 electron. So that 1 electron will be given to K shell, only K shell. So you write 1 under the K. After hydrogen, we have helium. Helium has 2 electrons. We have 2. The lithium is the next one. Lithium has 3 electrons. But don't forget that we said K shell can accommodate only 2 electrons. So meaning K will be given 2. Then we're having 1 more electron left. That one will be given to L. After lithium, we have beryllium. Beryllium is having 4 electrons. 2 will be given to this man. The 2 also will be given to L. And don't forget that L can accommodate 8 good electrons. So you continue to give L until it's 8. So after beryllium, we have boron. That is 2. Then we'll be having 4. 2, 3. After boron, we have carbon. That will be 2, 4. After carbon, we have nitrogen. That will be 2, 5. After nitrogen, we have oxygen. That will be 2, 6. After oxygen, you have fluorine. That will be 2, 7. After fluorine, you have neon. That will be 2, 8. So if you look at it in what we have here on our page, we have it. You see that hydrogen is having 1, as you can see, helium 2, then we have 2, 1 up till 8. Then immediately we get to sodium, we have 2, 8, 1 because we are having 1 more, that is 11 now. Magnesium 2, 8, 2, aluminium 2, 8, 3, silicon 2, 8, 4, and so on up till argon where we have 2, 8, 8. But when we get to potassium, we have 2, 8, 8, 1. Mind you, we said that this third shell, which is the M shell, can accommodate 18 electrons. But here we see us given it only 8. After giving it 8, we transferred 1 electron to N shell. This is due to Hofbauer principle. If you recall, we said in Hofbauer principle, as soon as we give 3p, we'll go to 4s. If you look at it, 3s is having 2 electrons according to what we have. 3p is having 6 electrons. If you add 2 plus 6, give us 8. So after giving 3, that is the third shell. After giving it 8, we'll go to 4s to give it 2. Then before we can now continue with 3d. So on that note, meaning if we are writing for potassium, potassium is going to be 2881, while calcium will be 2882. Then if you want to continue with the scandium, which is number 21, scandium will now be 2892, meaning you continue to give M until M is now 18. After scandium, we have titanium, which will be 28102. After titanium, we have vanadium. That one will be 28112. Up till you have 28182. Before you can now continue to give N 3, 4, 5, 6. So that is how we have the electron configuration based on shell. So let's look at the electronic configuration based on orbitals. That is, we are sharing the electrons into orbitals. As you can see, we have S, P, D, and F in this case. S, P, D, electronic configuration. Now, if you recall, we said we can give S, 2s after 1s, 2s, 2p, 3s, 3p, 4s. So if we give this shell, these orbitals, their electrons, we'll be having something like this. So sharing the electrons into orbitals, hydrogen that is having 1 electron, The first one will be given to 1s, as I told you. I will be having 1s2, the 1s1 first, that is for hydrogen. The helium, which is the second one, will be 1s2. And don't forget that we said that after you give it to 1s, you go to 2s. So the moment you come to 2s, you go to 2p. So the lithium, which is the next one, the 1s2, we have one more, that is 2s1 now. After the lithium, you have beryllium, that will be 1s2, then 2s2. After beryllium, we have boron, that will be 1s2, 2s2, 2p1. As I said earlier, that immediately we give it to 2s, we are going straight to 2p. Then after boron, we have carbon, that will be 1s2, 2s2, 2p2. After carbon, we have nitrogen, 1s2, 2s2, 2p3. After nitrogen, we have oxygen, 1s2, 2s2, 2p4. After oxygen, you have fluorine, 1s2, 2s2, 2p5. Then neon, which is number 10, 1s2, 2s2, 2p6. So when you look at the rest that we have there, if you look after neon, the next one is sodium. We have 1s2, 2s2, 2p6, then we go to 3s1. Then when we give 3s1, we give 3s2. Then after that one, we move to aluminium, which will now extend to 3p1 until you give p6. But immediately when you get to potassium, after we give 3p6, we are going straight to 4s1 instead of 3d. So we'll be having potassium to be 1s2, 2s2, 2p6, 3s2, 3p6, then 4s1. The same thing, calcium, which is number 20, is going to be 3p6, 4s2. Then if you want to now continue with scandium, which is number 21, it will now be 3p6, 4s2, then we'll be having 3d1. Then the titanium will be 3p6, 3d2, 4s2 until you give d10. When you get to zinc, that is when you stop giving it to d. So this is how electron is shared in orbitals, the spdf. In our next class, we'll be looking at the uses of these electronic configurations. And we'll look at some questions that we can also answer with that knowledge that we've had. Thanks for watching. Once again, I'm P Sam. Good day.